Good morning, dear students. We are going to discuss about Vizing theorem with some results. Now, we can go to the class. Today we are going to discuss about Vizing theorem. Before that, we will see some results. First, statement of the theorem is, let G be a connected graph. Then G has two edge coloring in which both colors are represented at each vertex of degree at least 2. Proof of the theorem. Let us assume that G be a non-trivial connected graph. Non-trivial connected graph means that G has more than one vertex. If G has exactly one vertex, it is called trivial graph. Here, G be a non-trivial connected graph. That is, G has at least two vertices. Suppose G is Eulerian. Here, Eulerian contains the Euler 2. It have an Eulerian trial which traverses every edges of G. Eulerian means that G is Eulerian if every vertex of degree G is even. If G is an even cycle means a cycle with an even number of vertices is called an even cycle. Then we have a proper two-edge coloring of G in which both colors are represented at each vertex of degree 2. If G is not an even cycle, then G has a vertex V0 of degree at least 4. Let V0, E1, V1, E2, etc. to E script C V0 and Euler tour of G. Here, G contains a Euler tour. Define the two sets. E1 is equal to edge EI, I is odd. E2 is equal to edge EI, I is even. That is, the edge set in the Euler tour can be partitioned at E1 and E2. That is, we have the edge in E1 by the color 1 and give the edge in E2 by the color 2. Then the two edge coloring E1, E2 of G has required coloring. Therefore, each vertex of G is an internal vertex of G, V0, E1, V1, E2, etc. to suppose G is non-Eulerian. Non-Eulerian means G contains odd degree vertices. Consider the first graph. We see the graph 1. Here these two vertices are odd degree. This graph is example of non-Eulerian. See the second graph. Now introducing the new vertex connecting to odd degree vertices. This is G star. Here in this graph G star, every vertex of G star is even degree. This is a Eulerian graph. It contains a Euler tour. We construct a new graph G star by introducing a new vertex V0 and joining it to each vertex of odd degree in G. Clearly, G star is Eulerian. It contains an Euler tour. V0, E1, V1, E2, etc. to V script C, E script C, V0. Define E1 is equal to edge EI, I is odd, E2 is equal to edge EI, I is even. Then edge colored with the edges E1 intersect E and edge E2 intersection E of G. This is the required property. Next we see definition of K-edge coloring. Given a K-edge coloring script C of G, let us denote the number of distinct colors represented at a vertex V of G by script C of V. See the graph. In this graph, only one color represents the vertex V1. So, script C of V1 is equal to 1. Number of distinct colors represent the vertex V2 is 2. So, script C of V2 is equal to 2 and so on. Script C of V3 is equal to 2 and script C of V4 is equal to 1. Next, talk about the proper K-edge coloring. If G is a proper K-edge coloring, then degree of V is equal to script C of V. Degree of the graph, degree of a vertex means the degree of a vertex of a graph is the number of edges that are incident to the vertex. In this graph, we give proper K-edge coloring. Adjacent edges are distinct colors. This graph is proper 4-edge coloring. In this graph here, degree of V1 is equal to script C of V1 is equal to 3. Here, the vertex V1, 3 edges are incident with V1. So, degree of V1 is equal to 3. And number of distinct colors in adjacent edges are represented at V1 is 3. So, script C of V1 is equal to 3. And so on. So, degree of V2 and degree of V3 and degree of V4 and degree of V5, and also find out the script C of V2 and script C of V3, script C of V4 and script C of V5. These are all equal. This graph is proper 4-edge coloring. Next we see the result. A K-edge coloring. Script C dash is an improvement of K-edge coloring script C. If sum of colors represent the every vertex in under the edge coloring script C dash is always greater than the sum of colors represent the every vertex in under the edge coloring script C. In this graph, green, red, yellow, here in V2, 3 colors represented. In V3, 2 colors represented. In V4, 3 colors represented. In V5, 2 colors represented. And V1 is only 1 color represented. So, sum of the colors represented the every vertex in under the edge coloring script C is equal to 1 plus 3 plus 2 plus 3 plus 2 is equal to the total sum is 11. And recoloring the same graph, here in this graph represent adjacent edges or distinct colors. Now, sum of the recoloring represent the every vertex in under the edge coloring. Script C dash of V is equal to 12. Therefore, the sum of script C dash of V is always greater than sum of script C of V. Optimal K-edge coloring. An optimal K-edge coloring is one which cannot be improved further. That is, proper coloring always cannot be improved further. That is, this is an example of optimal K-edge coloring. We need 4 colors this graph, and it is also proper coloring and it optimal K-edge coloring. In this graph, script C dash is an optimal 4-edge coloring. Next, statement of the theorem is if G is bipartite, then chromatic number of the graph chi dash is equal to maximum degree of that graph del. It is enough to prove that chi dash is greater than or equal to del. In bipartite, we have to prove that chi dash is equal to del. Suppose G is bipartite graph with the chi dash is greater than del. Let script G is equal to edge set E1, E2, etc. to E del be an optimal del edge coloring of G. Since chi dash is greater than del, it is not a proper coloring. This coloring cannot be proper. Not proper coloring means any vertex receive the same color that for adjacent vertices. Let U be a vertex such that script C of U is less than degree of U. In U, maybe one color is not represented and some color is represented more than once. Now consider del edge coloring at U. Some color I is not used and J is represented twice. By lemma, G contains an odd cycle, which is a contradiction. We consider a bipartite graph since bipartite graph has no odd cycle. We know that for any simple graph, chi dash is greater than or equal to del, therefore chi dash is equal to del. Next, Vizing theorem. Statement of the Vizing theorem. If G is simple, then either chi dash is equal to del or chi dash is equal to del plus 1. Proof of the theorem. Let G be a simple graph. If G is bipartite, then chi dash is equal to del. We need only to show that chi dash is less than or equal to del plus 1. Suppose that we take chi dash is greater than del plus 1. Let script C is equal to edge set is E1, E2, etc. to E del plus 1 be an optimal del plus 1 edge coloring of G. And let U be the vertex such that script C of U which is less than degree of U. Then there exists color I0 and I1 such that I0 not represented at U and I1 is represented at least twice at U. From this graph at U, that is I1 is represented twice at U, but I0 is not represented at U. Let U V1 have color I1 as shown in the graph A. Since degree of V1 is less than maximum degree of the graph plus 1, any vertex in G, degree of V is less than del plus 1. We used del plus 1 colors, certainly I2 or any color missing at V1. Some color I2 is not represented at V1. Now I2 must be represented at U since otherwise by recoloring U V1 with I2, we would obtain an improvement on script C. Thus, some edge V2U has color I2. Again, degree of V2 is less than del plus 1. V2U has color I2 since it is an improvement of script C. But we consider script C is the optimal del plus 1 edge coloring, it is not possible. Thus some edge V2U has color I2. Again, degree of V2 is less than del plus 1, some color I3 is not represented at V2 and I3 must be represented at U. Since otherwise by recoloring UV1 with I2 and UV2 with I3, we would obtain an improved del plus 1 edge coloring. Thus, some edge UV3 has color I3. Continuing this procedure, we construct a sequences V1, V2, etc. of vertices and I1, I2, etc. of colors such that first one is UVJ has color IJ. Second, IJ plus 1 is not represented at VJ since D of U is finite. there exists a smallest integer L such that for some k is less than L. Third is ik is equal to I plus I L plus 1. Since d of u is finite, there exists a smallest integer L such that for some k is less than L. Now we recolor G as follows for the vertices 1 less than or equal to I less than or equal to k minus L. U Vj with the color Ij plus 1 yielding a new del plus 1 edge coloring. Script C dash is equal to E1 dash, E2 dash, etc. to E del plus 1 dash of G. In graph B, now we have that is uv1 colored with I2 and uv2 colored with I3 up to etc. to uvj colored with ij. Clearly, script C dash of V is greater than or equal to script C of V for every vertices B belongs to B, and script C dash is also an optimal del plus 1 edge coloring of G. The component H dash of G of E I k dash union E I naught dash that contains U is an odd cycle. Now in addition U Vj with the color Ij plus 1 vertices k less than or equal to j less than or equal to L minus 1 and uv1 with the color Ik to obtain coloring del plus 1 edge coloring. Script C double dash is equal to E1 double dash, E2 double dash, etc. to E del plus 1 double dash as the following the graph C. Script C double dash which is greater than or equal to script C of V for every vertices V belongs to V and the component H double dash of G of E I k double dash union E I naught double dash that contains U is an odd cycle. Here in this graph C, H double dash is an odd cycle. H double dash is an odd cycle. U V k minus 1 I naught and again I naught to V1 to U. H double dash is an odd cycle. But since Vk has degree 2 in H dash, clearly Vk has degree 1 in H double dash. But H double dash is an odd cycle contains U, which is a contradiction. This proves that our assumption is wrong. Thus, chi dash is greater than or equal to del and chi dash is less than or equal to del plus 1. Therefore, chi dash is equal to del and chi dash is equal to del plus 1. Hence, if G is simple, then either chi dash is equal to del or chi dash is equal to del plus 1. Hence, complete the proof of the theorem.